Okay, there's another one that is also related to the sessions between the TCP sessions that is called session protection. This is not a protection mechanism in terms of protecting traffic black holes. This is a reconvergence optimization of LDP when the neighbors go down and then the neighbors come back later. So the idea is that when a neighbor goes down, you flush all of their labels out of both the label forwarding information base and the label information base. So like in this case here, between router 1 and router 2, we're running labeling. Okay, LDP is working and IGP is working. We saw this when we looked at the show MPLS LDP bindings. And let's say pipe include 2222. Okay, these are all the different label numbers that we're learning from router 2. Okay, now the interface to router 2 goes down. This means we lost ISIS adjacency and we lost the LDP peering because we were peering over that directly connected link. Okay, the end result is now when we look at the show MPLS LDP binding, we remove all of their labels. Same as when we show MPLS forwarding table, there should be no outgoing interfaces that are listed as gig 1.12. Now this is what you would expect. It's the same as regular IGP convergence or BGP convergence. If the link between the neighbors go down, you should withdraw the routes. Then when the link comes back or the neighbor comes back, you go to reinstall the routes. You do the label exchange again between the neighbors. So here in this case, the neighbor comes back. So we go to router 1 and re-enable the link. We should see that ISIS comes up and then LDP comes up. And if we now show MPLS forwarding table, pipe include 1.12, we can see now we have labels that are out that interface. And if we show MPLS LDP bindings, we can see that we are receiving labels from router 2. But if we compare this output here to what we previously had seen when we were receiving labels from router 2 earlier, we should see that basically it's the same output. So when we look between these two tabs, basically there's nothing changing in the output here. So starting at whatever routes that we were learning from router 2, they typically retain the same label numbers when they go to reconverge. So the potential problem with this is then if there is a temporary flap between the neighbors, it's going to cause them to withdraw the LDP labels, then add them back. Then withdraw the labels, add them back over and over and over, and we're still reconverging the same label number again and again and again. So one of the optimizations for this is to say, well, when the neighbor goes down, you can flush the information out of the LFIB, because I don't want to actually forward towards the neighbor, but I'm going to keep the information cached in the lib, in the label information base, or basically which is the label database. So as long as I'm not actually installing them for forwarding, it's not going to cause a traffic problem. But when the neighbor comes back up, I don't need to renegotiate every single label number. So it's a reconvergence optimization. And specifically the way that you configure this is you say under, I believe it's globally, MPLS LDP session protection. Okay, you can say for what particular peers, or in this case, I'm just going to say globally. LDP session protection. Same thing on router 2. So globally, MPLS LDP session protection. And let's say the same thing on XR1. So under MPLS LDP, we'll say session protection. So it's pretty much the same syntax, it's just under the MPLS LDP mode. Okay, we commit the config, and then on router 1, we look at the show MPLS LDP neighbors, and let's look at the specific neighbor. So 2222 detail and 111111 detail. Okay, it now says session protection is enabled and the state is ready. This is for XR1. Okay, likewise for router 2, it says session protection is enabled. State is incomplete though. Okay, this means for some reason they didn't fully synchronize. So let's say for router 2 detail, protection is enabled, state is incomplete. Why would that be the case? This may be, actually no, I know why this is. This is because on router 2, we're using the interface as the transport source. Okay, we need to use the loopback as the transport source. Okay, so next on router 1, we should see that the, let's clear the neighbor. Clear MPLS LDP neighbor 2222. Neighbor is down, neighbor is up. Okay, state of protection is ready. Okay, so next thing that happens, same as before, there's a failure between the two neighbors. So the link between router 1 and router 2 go down. But before we do this, let's look at the show MPLS forwarding table, pipe include 1.12. Okay, we see that there are labels installed. And if we look at the show MPLS LDP bindings, pipe include 2222, we're currently learning labels from router 2. Okay, this is the default state. Right now, everything is working. Okay, next, the link fails between them. What we should see is that now session protection kicks in. It's saying that I lost the directly connected link to router 2, but I still have an alternate route to them. Because if we look at the show IP route for 2222, we've now rerouted that path through somebody else in the middle. So over to router 2, we send them a message and say, hey, there was something wrong with the session direct between us. But now we have the protected session that is essentially a multi-hop TCP session between router 1 and router 2. Now, in terms of forwarding traffic, we're not going to keep the labels installed because that interface is gone. So we don't have gig 1.12 in the forwarding table. But if we look at the show MPLS LDP bindings, we're still going to keep or cache the label information that we learned from router 2. Now, eventually, at some point, this information is going to get flushed out. There's a separate timer that you can set for the session protection. But the idea now is that when router 2 comes back, I'm not going to have to do reconvergence with them. I'm just going to say, hey, are all the label numbers the same? And they agree on it, and then we can install them back in the forwarding table. So now on router 1, the interface comes back up. And actually, before we do this, let's look at the show MPLS LDP neighbor 2222 detail. It says that protection is running, and the hold time is currently this. Okay, so you can see it's a long value there by default, 86,000 seconds. And if we then say no shutdown, we should see the IGB neighbor comes back up, the LDP neighbor comes back up, and it says, okay, now the session's recovered. Session's recovered because if we show IP route 2222, it's now going to that directly connected link. Well, once it reconverges, it's going to that directly connected link, which is where the discovery source is for router 2. So now when we look at the show MPLS forwarding table, we should found that we reinstalled the labels from the lib to the lfib, but the labels that were in the lib to begin with, which is the show MPLS LDP bindings, we didn't have to flush those out. So again, the only optimization of this feature is of reconvergence. It's when the neighbor goes down, you don't flush their labels out of the binding database. Then when they come back in, you can say, okay, now if IGP agrees that these are the best routes, we take the intersection between those, and that's what goes into the actual label forwarding database. There's a question, does the lib and the lfib get the routes from the IGP database or the routes from the routing table? It gets it from the routing table. So this means that if you learn the route through ISIS, but for some reason you're installing the route through another protocol, the label will not be valid. And we will see cases later where that is a problem, that you have to look at what is the route currently installed in the routing table as before you can actually use it. So what I mean by this is, let's say that we have an IGP adjacency between router 1 and router 2. Okay, we're running IS to IS. IS to IS has an administrative distance of 115. Okay, then router 2 and XR1, they form an eBGP peering, and XR1 and router 1 also form eBGP. Router 2 is advertising its loopback into ISIS, and it's also learning it into eBGP. This means that router 1 now also knows the route through eBGP. eBGP has a distance of 20. So this means that the IGP route, the ISIS route, gets flushed out, the BGP route gets installed. Now, unless I'm learning a label through BGP, it means that there's no longer an intersection between the lib and the rib. So the routing table plus the label routing table. The end result is that they can't match up together in order to be installed in the label forwarding table. So in other words, you cannot use a label in order to reach that particular destination. So again, where you would see this is typically when there's multiple protocols that you're learning the routes from, but you're not using labeling for both of them. And we will see this in more detail when we go through inter-AS L3 VPN. For intra-AS, you normally don't run into this case in a proper design because you typically just run IGP everywhere and run LDP everywhere, and then the labels and the routes should always be on a one-to-one basis. But it's only when you have multiple different routing protocols that you have to worry about, well, where did the route actually come from? Did it come from IGP versus BGP versus traffic engineering? And then do I have a label number that's also associated with that? Okay, beyond this, so there's some other miscellaneous features. I'm not going to go through these in terms of configuration examples for all of them, but there is a feature where we can configure the label ranges. If you want a specific router to use a specific range of numbers for the labels, you'll see that by default in regular iOS, when we look at the show MPLS forwarding table, all of the routers start at the lowest number in the range, which is label number 16, and they start counting up from there. So on routers 1, 2, and 3, basically you'll see that the local labels are about the same numbers. When we look at iOS XR, it starts at 16,000 and counts up. Show MPLS forwarding table. But this is an option that you can change globally for LDP. So what we'll do a little bit later when we're looking at the L3 VPN verifications is that I'll change these label numbers based on the router number to make it a little bit easier when we're looking at the label to correlate that to what router it actually went through. So for example, on router 1, we could say the MPLS label range is going to be 1,000 to 1,000 to 1,999. It says this will cause these dynamic labels to go out of range. Okay, that's fine, but the problem is they're currently allocated. So in order to get this to have an effect, you need to reboot the box. The other option would have been to change the label range before I actually did any adjacencies. Then when I do the allocation, I would start by using that number. So if you are using this, note that there is an order of operations that you need to think about. You would want to set the label range before you start LDP, because otherwise LDP is going to use numbers that are not actually configured. Okay, if we show MPLS forwarding table, notice it's still using those numbers 16, and if we clear MPLS LDP neighbor star, when the neighbors go down and then the neighbors come back, when we show MPLS forwarding table, it still did not change the label numbers. So it is disruptive to set this, or excuse me, it's not disruptive to set it. You would need to reboot the box in order for it to actually take effect. Okay, the other case that this is needed is if you're doing a static label assignment, and it's like a static route, but you have to do the static route on a hop-by-hop basis to connect the input label and the output label together end-to-end. And in order to do this, you need to assign a range for static labeling. So specifically in iOS, you would say there's an MPLS label range, let's say 9999 to whatever, 10,010, and this is for static bindings. Okay, otherwise, the static bindings don't have numbers to do allocations from, and it doesn't allow you to do a static label. But 99% of the time, you're not going to use static labels. You're either going to use LDP, BGP, or RSVP for MPLS traffic engineering. Okay, beyond that, one of the other important features of LDP in terms of like a scalability technique is to limit what labels we're doing allocations for. So we talked about this briefly before, similar to how you would filter what labels you are advertising. In most realistic cases, you only need the labels for the loopbacks of the PEs. So this means that when I create the label numbers, it doesn't make any sense to label every single IGP route because I don't need those installed in memory. I'm not going to do label switching towards them. So what you would typically do in a lot of cases is to say globally that I want to change the MPLS LDP. I think you go to the label mode, MPLS LDP label, and then you say allocate global host routes. So if we show run section LDP, it is going to be this. Okay, so on routers 1, 2, and 3, we're going to say MPLS label allocate global host routes. And then under iOS XR, we'll say under MPLS LDP, the is it under address family, IPv4? Label local allocate this. Allocate for host routes. Okay, so if we show config, it's under MPLS LDP, address family, IPv4, label local allocate for host routes. So if we apply this config on XR1, 2, and 3, then the final end result on all of these devices, when we look at the show MPLS forwarding table, is that the other routes, and these will eventually get withdrawn. It takes a minute for, to get them out of there. But the non-loopbacks will eventually leave the table, and we're only doing labeling between the /32s of the routers. Now, as someone had asked the question here, is this the same as doing prefix suppression? It's the same result in terms of the labels, but there's a difference in IGP reachability between them. Now, in terms of prefix suppression, that is an IGP function that you could say, like in ISIS, that I only want to advertise the loopbacks. So I'll advertise the loopbacks of 1, 2, and 3, but I won't advertise the transit interfaces that connect the routers together. Now, the reason we don't need to advertise the transit interfaces is because we're not sending packets to those links. We're only sending packets through those links. So as long as I have the label or the route for the loopback, I can do allocation for everything, and the end result is that we're only doing allocation for the loopbacks. And where you would specifically see this is under ISIS. We say to do, and it's different. I think in XR it's global. Let's see if it's at the link level in iOS. Gig 1.12, IP router ISIS. There's an ISIS. I think it is this. It's no ISIS advertised prefix. Let me double check the command reference. Okay, so let's look at this under routing command reference for OSPF and for ISIS. Okay, under OSPF, it is the command that is just prefix suppression. Prefix suppression. To prevent OSPF from advertising all prefixes except prefixes that are associated with the loopbacks. Then under ISIS, oh, it's advertised passive only, that's what it is. Configure ISIS to only advertise prefixes that belong to passive interfaces, use this. And typically your loopback is the one that is passive, so the other transit interfaces, we stop advertising them. So let's say that we undo this change where I had changed the label allocation, show MPLS forwarding table, we see we have just the loopbacks. Okay, we go back to the default behavior, which is under MPLS LDP label, that we say no allocate global host routes. Okay, so on all of these, MPLS LDP label, no allocate global host routes. on router 1, 2, and 3. Then on XR, we'll say to, here we'll just abort those changes. Abort that commit, same as here. Okay, that's why it didn't take effect, because I didn't commit the change. Okay, next let's look at the show MPLS forwarding table. Okay, now we have all of the routes again. But next we go under ISIS and we say advertise passive only. So this is on router 2 and router 3. Okay, under iOS XR, it should be the same thing. Router ISIS 1. Under address family, IPv4 unicast, we say advertise passive only. Okay, so this is the same on XR2 and XR3. Okay, if we now look at the show MPLS forwarding table, the end result is that we have the labels only for the loopbacks. But the difference now is when we look at the IGP table, IGP likewise will have only the loopbacks. So if we show route IPv4 unicast, this is on XR, it says we have the connected links plus we have these 5 loopbacks, 1, 2, 3, 5, and then 11, 12, and 13. From iOS's point of view, same thing, show IP route ISIS, we have just the loopbacks. Now, from a functionality point of view, this doesn't affect the MPLS label switch paths that are going through the core. This is simply an optimization of the IGP database. Because from router 1's point of view, let's say like we want to do SNMP polling of one of the other boxes. Let's say we want to do SNMP polling of router 3. Well, I don't need to poll it on this interface, and this interface. I can just poll it on the loopback. And from one's point of view, as long as I ping 3333 when I'm sourcing my packets from the loopback, I'm able to reach them. It's only an issue that when I ping them from my connected interface, since router 3 doesn't have a route back to that, we won't be able to get connectivity, but again, we don't need it because we're only sending traffic through the router, we're not sending traffic to the link that is directly connecting them. So again, the functionality is kind of the same end result if you're doing either prefix suppression in IGP or if you're doing label allocation filtering in LDP. The main difference being is that this one here is only an optimization of LDP itself. It's not an optimization of IGP. Okay, the other one, which is less common, which is the label advertisement filtering. This was implemented before they had the function to do the allocation filtering, and this one can be dangerous because there can be a device in the middle that you're learning a label from somebody else and then you filter it out from the other neighbors. So for example, like if we were to go to router 2, and router 2 is going to say, when I get a label in from 3's loopback and I'm supposed to advertise it to 1, if I drop this advertisement, it means that 1 will send the IGP traffic that way, but it will be unlabeled. And we could run into that same case as I was describing before. You black hole traffic in the core because the core doesn't have an end-to-end label switch path. So what this would look like would be on router 2 if we said no MPLS LDP advertise labels. MPLS LDP advertise labels for, and you say for these specific prefixes. So let's say for 99, access list 99 says permit 2222, permit 11, 11, 11, 11, etc., whatever all the loopbacks that we want to advertise. And if we now look at router 1 and show MPLS forwarding table, 3333 now has no label because we're doing an advertisement from 2 to 1, but the advertisement has no label number associated with it. So the end result is that you cannot do label switching towards it. And again, when you look at this output, this is a very important point. There is a key difference between where it says pop label versus no label. If it says pop label, it means you're taking one label off the stack and then forwarding the packet on. If it says no label, it means you're removing the entire label stack and forwarding it on. Or in other words, you're not using MPLS in order to reach that particular destination. So again, in most cases, you would not do it this way, where you show run section MPLS. You would not do a filter like this. You would be better off doing the allocation filter on the one who originates the label. But you have to figure within a troubleshooting environment, this is definitely something that they could throw at you. So maybe you have a connectivity problem end to end between the customer sites, and then it finally boils down to, well, it was an issue that the label for the PEs was not being advertised within the MPLS core. And once we get into more details of MPLS Layer 3 VPN, we'll get into this with specific examples and see, well, how do we actually track this down on a hop-by-hop basis? If I see the control plane and I'm receiving the routes, but for some reason I can't reach it, you need to know exactly how all of the pieces of the puzzle connect, because otherwise there's way too many devices that you would need to look at the running config to sort through what the particular problem is. Okay, there's a question, if we advertise only the loopbacks, how does this impact the advertisement of LSAs in the SPF algorithm? It simply means that in the payload of the LSA or the payload of the LSP, you don't describe the IP addresses of the other links. So when we look at the ISIS database now and we're doing the prefix suppression, so let's say on all these routers, show run router ISIS or show run section router ISIS. Under iOS, we said advertise passive only. In iOS XR, we said advertise passive only under the address family IPv4. If we now look at the show ISIS database detail, if we look at the specific IP addresses that are in the topology, it's only advertising the loopbacks. But it's still advertising what are the connections in terms of the shortest path graph. So router 2 is telling everyone else, hey, I'm connected to router 3, to XR2, to XR3, to XR1. And then when you solve the shortest path tree, these are the metrics that I'm assigning to these particular adjacencies. So from router 2, you can reach router 1, XR1, XR2, etc. But in terms of IP addresses, you can only reach 2222. And we'll see that this is a key understanding for shortest path first, that there is a distinction between the graph of SPF and the application data that you're advertising, where the application data is the routes. So once the graph is formed, then you say, okay, well, what is attached to the graph? Attached to the graph is 2222/32. And if I'm on router 3, I know router 3 is directly adjacent with router 2. Look at whatever the metric value is, and it implies that I can reach this particular destination. And we'll see that this is the same case when we're looking at MPLS traffic engineering, because we're going to use the SPF topology to run a constrained shortest path first, or a CSPF, and then the attributes of CSPF are going to be things that we define in traffic engineering, like what is the affinity, what is the shared risk link group, what is the traffic engineering metric, what is the bandwidth value, what are the differentiated service, the DSCP, or for diffserv tunneling for TE. These are basically all attributes of the graph, and we'll see eventually these are going to all appear here in the database. So this applies, correct, there's a comment here, so this applies only to ISIS. No, it does apply to OSPF, it's both. So in the case of OSPF, it would look like this. If we said just router OSPF1, network 0000, 255, 255, 255, 255, area 0, and then that would be on a regular iOS. Okay, so regular iOS is running OSPF everywhere. And then we say prefix dash suppression. So let's give this a minute for the routers to establish adjacency. And I enable this on everyone, so basically it should be these 4 plus these 4, okay, plus router 7. We should have OSPF running end to end between all of these. If we show IP OSPF neighbors, okay, we have the adjacencies. If we now show IP route OSPF, we're learning just the loopbacks because we suppressed all of the other prefixes. But again, as long as we're sourcing and destining the traffic to the loopbacks, then we're able to route the traffic through the shortest path tree. Whereas specifically, if we look at the database of OSPF and show IP OSPF database detail, or no, show OSPF database router, this is describing what are the links in terms of the adjacencies. So these transit networks are talking about LSA2. And then we have the stub networks. These are the actual routes. So the routes we're advertising are the loopbacks 2222, 22, 22, 22. And then we're saying this is what the graph looks like. So it's different syntax, but it's the same logic. This says don't advertise the IP addresses of my connected links except for the loopbacks. This says advertise only my passive interfaces, and my passive interfaces are going to be the loopbacks.